All right, so we're using Axler, the third edition. Okay, the latest edition I think is the fourth or maybe even later, but we are going to stick to the third edition because in the later editions, there's more material and then we have to, skip sections and so on. Here, we're just going to do it sequentially. Okay, so make sure you're not reading from the wrong text. All right, so let's start then. We're going to start with invariant subspaces. So the text is going to use the notation of direct sums. Okay, and this we sort of saw very briefly when we were doing Hoffman and Kuhn. So let me just quickly give you the definition. So a direct sum is basically as follows. So suppose U1 to UM are subspaces of some vector space. Okay. Then the sum U1 to UM is called a direct sum if, so let me write it. So U1 to UM be subspaces. Okay. Then U1, this sum, right, is called a direct sum. Are you asking a question? Something unclear? Tell me. Say it louder. If we have not seen this before. It's Axler, yeah. That was often influence. That's what I was saying in the beginning. Yeah. Okay, and make sure. So the important thing is, since you missed that it's a different textbook, I should also emphasize you have to look at the third edition. Okay, do not look at the fourth edition or the ones afterwards. The topics are slightly different from it. Any more questions? Okay. Right, so let you. Okay, so U1 to UN is the subspaces of this vector space B. Okay, and U1 plus U2 all the way to UN is called a direct sum. Okay. If each element of U1 plus UN can be written in only one way as a sum of these vectors, U1 plus UN, where each Uj is in the vector space. Uj. Okay, the definition making sense? Yeah, so it's sort of immediate. If you have like an overlap in the subspace, right, then of course you can write it in many ways because you can just have many different linear combinations of vectors. So it will not be unique. So for it to be unique, you sort of have to have some kind of a direct sum structure. What's the question? Each divide would have a distinct basis, like a historic basis. You can do that, and that should be enough. I don't know if it's necessary. We will probably have to check the statement. Probably. Intuitively it looks that way, but maybe that catches. Okay. Yeah, yeah. Exactly. So the sum is exactly the same, is defined exactly the same. But to be a direct sum, like you said, it has to be unique. That is the main thing. Okay, so it can be written only in one, right? So that is the subset. Is the statement clear? Okay, so let me give you a quick example. So suppose that you have, say, yeah. So let's say you have this as is your first vector, epsilon1, epsilon2 as your second vector, right? Epsilon3 as your third vector. Okay, so we can take the span of epsilon1, epsilon2, okay, and we can take this to be say u1, and let's take span of epsilon3 to be u2. Okay. Yeah. So these are two spaces. So now if you want to write a sum, so if you write u1 from u1, u2 from u2, okay, it would have a form of this thing, right? Like it would have non-zero entries, let's call it AB and then C. So these AB are going to come from vectors in the space U1, and this is going to come from the space in U2. Okay. So that is sort of the idea that you can, and then this would be unique. Because here it's a basis, it's kind of trivial, but that is sort of the idea. Okay, is it clear to everyone? Yeah, at the back, is it making sense? Okay. All right. So yeah, okay. So okay, this is exactly the example, right? So here xy in F3, this is what they're calling U. So W is 0, 0, Z. This is exactly the example that I just listed, right? Okay. Yeah, so I think the remaining things I thought we might need, but for now we can skip it. Okay, so I'll probably maybe give you a few exercises to get some sense of it. But for now, I think this is sort of enough. And then let's actually start the chapter. Okay, so now the goal of this chapter is to develop tools that help us understand the structure of operators. Okay, operators, remember, are linear maps from the vector space to itself, right? This is it's basically just a linear transformation from a certain vector space to itself. So those are called linear operators, or just operators. Okay, and we want to understand the structure of these objects. Okay, and we're going to use the notation here, which we've been using before, right? LV for LV comma V. That is it. So now suppose you have some linear operator T in this space of linear operators, and we have a direct sum decomposition. So this vector space can be, there's a decomposition for the vector space, right? Exactly in the sense that I described, right? Did I not introduce the O plus notation? Sorry, again. I forgot to mention one thing. So, okay, so we were using this plus notation, right, for defining the sum of vector spaces. This we already saw, right, as Emmanuel, is it? Emmanuel had mentioned, right? We saw it in one of the previous chapters that you can write this sum. And now if you have the extra, if you have this extra property that any vector can be uniquely written, right, in terms of vectors in each of these spaces, right? So if it is indeed a direct sum, then we actually emphasize this by writing the sum as such with this O plus notation. Okay, so whenever you see this O plus notation, what it means is that each of the vector spaces, each of these subspaces are such that any vector in this direct sum can be written uniquely in terms of these. Is that okay? All right. So now using this direct sum notation, it is saying that suppose you have a vector space V, right, which admits this direct sum decomposition. Then to understand the behavior of T, we need only understand the behavior of each linear operator restricted to this subspace. Okay, is this making sense? What is happening? So remember the example, right? So there was like XY and then there was Z. So now what we're going to do is we're going to restrict the action of U onto this subspace V and onto the subspace W in order to understand what's happening. Is that okay? All right. Okay, so here we introduce this notation T sub Uj, which is saying that you restrict T to the smaller domain U sub J. Okay. So now dealing with T sub Uj should be easier because it is a smaller vector space than V. So the intuition is you want to understand the structure of the operator, and what we're doing is we're trying to understand it by understanding it on smaller, simpler blocks of the vector space, rather than directly trying to understand it on the big vector space. In each UI, if an element is present, then it would only be in the span of that vector space. So, okay, so if you have U, and you have some vector little u in U, so say this is U1 or some UN. Okay, so if U belongs to UI, what is your question then? No, it's in the span, right? Like for example, here, right? So we had 1, 0, right? And we had 0, 1, 0. Okay, first of all, is the question clear to everyone? So the question that wait, what was your name again? So the question that Manan asked was the following. So he said, suppose that U is a vector in one of these UIs, right? He was asking, does U necessarily have to be a basis vector? Okay, that's the question. And you can define any vector to be a basis vector, right? That is possible. You can take one vector, you can extend it and make it into a basis. That is always true. So the question is not quite well defined in that sense. But I guess what you meant to ask is probably that if I fix some basis using which I define these use does little u belonging to capital UI mean that it has to be one of those vectors? It doesn't, right? It's just a span. So for instance, like we defined u to be, say, span of epsilon1, epsilon2, right? And w was the span of epsilon3, right? So now, obviously, it can be any vector in the span of, oops, it can be any vector in this span, right? It doesn't have to be epsilon1 or epsilon2, right? Because in U you have exactly one vector, right? That's all it's saying. But so whenever you write a vector V, okay, let me write, what do I call it? Let's call it a vector A, right? It would be some alpha of U1 plus beta, I shouldn't call it, let's call it B and C. So some scalar times U1 and some scalar times U2. And U2 would, well, let's just call it W actually. Let's do that. So let's call this U, let's call this Y. Okay, so this belongs to capital U, this belongs to capital W. So all it is saying is that these coefficients are going to be unique and these vectors are going to be. Actually, we can even drop this since it's a vector. We can just absorb the scale. So all it is saying is that this U is going to be unique in the vector space. That is it. Is that clear? Any other question? Looks that way. Yeah. I don't remember the full proofs. Intuitively, yes. That's what I think Manuel was also asking. Because if they have overlap, then you can write it as linear combination and it will mess things up. So that should be nice. Any other questions? Folks at the back, is it making sense? It's a new chapter, okay? So try to make sure you're following because it's a fresh start. We don't want to repeat the same mistakes again. All good? Yeah? Okay. So let's continue then. So however, if we intend to apply tools from tools that we developed in the study of operators, then we have a problem, right? So what is the problem? The problem is that when you apply T to vectors from U sub J, they might give you a vector that doesn't belong to U sub J, right? There is no guarantee that you would stay inside that same subspace. Does that make sense? Okay. So basically what it means is that the restriction of T to the subspace may not actually be an operator, right? Because an operator takes from one space to itself. Here it might take you from one space to something outside of that space. Yeah? No, is it making sense? Yeah? All right. So this suggests that we should only consider decompositions of V of the form above, where these maps, where T maps UJ to itself. Okay. Making sense so far? Okay, so the idea was to understand T. We said suppose the vector spaces of this form, right, plus. Okay, and now we're going to look at restrictions of T to these spaces UI, and we only want to consider those T's for which this results in something that is also inside U. Okay, or a subset of U. That's what for UI. Okay, all right. So this brings us to the definition of what we call an invariant subspace. So let T be some linear operator. The subspace of U of B is called invariant under T if so a subspace of U, subspace U of V is called invariant under T if U belonging to capital U implies TU belongs to capital U. Is the definition clear? Any questions about the definition? At the back, is it okay? Is it making sense? Can you tell me your name, the person with the laptop? Yeah, you, yes. Can someone repeat the name? I can't hear him. Adar? Adar, is that it? Something like this? A-E? Oh man. now, I think that's probably going to be easy because I can't hear all the way. Okay. Well, it's AD, you're my representative, okay, for that section, because otherwise it's hard for me to follow. People are too shy, right? So hopefully they'll become more comfortable over the days. But as of now, I'm going to look at you and you have to answer for everyone. Okay. So is it making sense? Is the definition okay? All right. Okay. So now let's look at example 5.3. So the example is saying the following. So it says, let T be some linear operator. Okay. Then each of the following subspaces are invariant under T. Okay. So the first one is the space of zero vectors. Okay. Is it clear that it's invariant? Yeah. Okay. Why is it invariant? AD. Why is it invariant? Exactly. Okay, so the answer is that if I apply any linear operator T on the zero vector, by linearity, right, it has to be what? The zero vector. Okay. So what is it doing? It is sending the zero vector, the subspace 0 to itself. Okay. All right. What about the entire vector space V? Exactly. It's a linear operator, right? So any vector U, so U in V, any vector, this will be inside V. It cannot go outside by definition of a linear operator. Right? These are completely trivial things. I'm just making sure that the notation is clear. Okay. What about part C? The null space of T. Okay, so what is the definition of null space, first of all? The set of vectors such that alpha is 0, right? So now T acting on alpha gives you 0. Yeah. And 0 is what? Does it belong to the null space? It's okay then? Okay. Similarity range. Okay. Everything has to be in the range. So you cannot go outside it. So in particular, if you restrict two vectors in the range, they will also map to this. Is that okay? Yeah. So let's go through it together. So suppose you have some vector U in the range of V. Okay. You apply the linear operator T on U. This vector has to be, can it be outside the range of T? What is the definition of range of T? The vector that have corresponding vector. Exactly. So it's TU such that U belongs to V. Okay. So it's okay. Okay. Any more questions? Okay. Range of T, yeah. So let's do it, right? So suppose U belongs to the range of T. Okay. The question is, does TU also belong to the range? Question mark. It cannot go outside the range, by definition, right? It has to stay inside. Okay. Any other questions? AD? Good. Okay. Yeah, maybe we should also have a representative here. What's your name? Tell me. Oh man. I'll call you S. Sorry, it's just easier. Okay. Which one? For B? Okay, let's do that. So suppose there's a vector U that belongs in the vector space. Right? You apply the operator T to U. Okay. Now this operator, this vector, does it or does it not belong to V? Okay, so you answered your own question. Okay. Maybe we can have someone from that corner. Does anybody want to help me from the corner? Everyone's trying to look away. Okay. Okay. All right. So we have AD and S. That's good. ADS. Good. Yeah, I was laughing because this is like some ADS CFT stuff. Anyway, okay. So story. All right. So must an operator T have any invariant subspaces other than 0 and V. Okay, so we established some very trivial subspaces, right? So we said that there's a 0 space and there's a V space. The question is, can there be other subspaces? And later we'll see that the answer is yes. Okay, so if V is finite dimensional and the dimension of V is strictly greater than 1, then we will have a non-trivial subspace. And when the field is complex and when the dimension of V is strictly greater than 2, then also we'll have a non-trivial subspace when the field is complex. Because we'll see these things later. So all of this to say that you're guaranteed, at least in finite dimensions, to have some interesting subspaces that will be preserved by the operator. Is that okay? Well, okay. So why don't the null space of T or the range of T suffice to answer this question? Right. So one might think that, because we are looking at the set of things that are mapped to 0 and the set of things that are, in the range, maybe these are enough to sort of say something non-trivial about the existence of some other subspace. But it turns out that, there are a few things. So one is that the null space itself might just be 0, right? So it doesn't really say anything non-trivial potentially. And the other thing is that this range may be equal to V. Right? So sometimes linear operators can span the entire thing. So in both cases, what we thought were non-trivial subspaces, at least in some sense, right? So 0 looked like, the null space and the range look like, they could potentially give you some information about the linear operator T, but they could also be completely trivial because the null space can just be 0 and the range of T could be the entire vector space. Okay? So it's just motivating why we need to work harder and look at what are the interesting subspaces. Okay. All right. So now we're going to use the notation PR to denote the vector space of polynomials over the field R. This we've seen many times. P4 is the basically polynomials of degree at most 4. This is very similar to our previous notation. And if P is P prime, if P is a polynomial, P prime is used to denote the derivative. These are standard things that we've seen. I'm just introducing them for the example, okay, to sort of get some handle on interesting subspaces. So suppose that T is a linear operator on polynomials, okay, and it's just a differentiation operator. Okay. Then the claim is P4 is a subspace that is invariant under T. Is that clear? Okay, I'll give you a second, not a second. I'll give you 30 seconds to think about it. It's very straightforward.
We have not the earlier statement that it must be in variance of every entity.
Yeah, we'll do that. That's incomplete. We're just motivated. Because the question was, we haven't proved that there would be some non-trivial subspace, but we'll do it. Is it making sense in areas? Yeah, that part I also haven't tried it. So we'll come to it. But most likely it has to do with the fact that the field has more it has more degrees of freedom, right? There's the real part and the complex part. So that's my guess. We'll see. Okay. Is the example clear? Okay, who wants to answer why this is a subspace? Why P4 is invariant under T? Okay, anyone else? Is it not clear? Okay, you have to ask you guys if it's not clear. You cannot let me go on. Okay, it's very important if some things are not fully clear. If they are clear, I mean, there are many people who would understand immediately. That doesn't mean anything. Just pretend they don't exist. Okay, you're the only student in the class, and I'm the only person teaching you. That is how you should think. And if something is not clear, do not let me proceed. These other people have plenty of other material to read. They will read. They will not get bored. Okay. Okay. So what was the question? The question is, we want to prove that with what is your name again? L, right? Close enough? Okay. So you're the representative for that section. Okay. Good. All right. So let me check. 80, was it clear for you? Okay, good. So L's question is, why is P4 a subspace, invariant subspace under T? So let's see. So let's take some polynomial P of degree at most 4, okay, over the real numbers. So P4 is just saying polynomial of degree at most 4. R is just the field, the real numbers. Right. So now when you have T acting on P, okay, what is the degree of this polynomial? This will give you a degree at most what polynomial? At most 3 actually, because it's differentiation, but let's say at most 4. That is also correct, right? So it is at most because it's derivative, but let's say at most 4 polynomials. Okay. What is the definition of P4? Right. So this is going to be, sorry, this is going to be a subset of, this is actually, right. And how do you show something is it in invariant subspace? You show that all vectors in that subspace, when T acts on them, they stay inside that same subspace. Yeah. Okay. So you answered your own question, right? Okay. Clear to everyone? But who was S? Was somebody called S? Ah, yeah. Is it here? Okay. ALS. Good. All right. So example 5.4 is fine. So can we continue? Yeah. Yes. Exactly. Exactly. So it's invariant meaning T leaves that subspace invariant. Exactly. Exactly. Okay. So and also you're fixing the subspaces, right? In a certain sense. So they're both exactly. So sorry, say your question again. Let me write it down. Say it slowly. Yeah, so you have only one subspace at this point, right? So we did prove the fact that yeah. So the point good. So okay, so let me quickly say this. So the question was is P4 a part of a direct sum decomposition? Right? It's a reasonable question. Is the question clear? Okay, it's one of the things. So if you take any subspace, you can find the remaining, you can find like something else that sort of makes it into a direct sum decomposition. So it's almost like a vector. Like if you give me one vector, I can extend it to a vector space. It is similar. If you give me one subspace, I can construct another subspace such that the direct sum of the two would give you the initial subspace. Okay, we didn't prove it. We don't really need it, but it's good to keep it. Okay, so besides that question, is everything okay? All right. So let's continue then with eigenvalues and eigenvectors. So we return later to a deeper study of invariant subspaces in general. Okay. For now, what we're going to do is we're going to focus on the simplest possible non-trivial invariant subspace. Because we're going to look at the simplest. So we already said we want to simplify the vector space. So we started looking at the direct sum decomposition. Now we're saying that not only will we do the direct sum decomposition, but we'll actually think of one very simple vector space which has dimension 1. That's what we're going to focus on. Okay. So let's do that. So we're going to focus on invariant subspaces of dimension 1. That is the focus. Right, so you take any vector v in capital V such that it's non-zero and let u equal the set of scalar multiples of v. Okay, so u is lambda v, which is essentially the span of v. Is that okay? All right. Then u is a one-dimensional subspace of v. Not said anything non-trivial so far. Right? You take one vector, you scale it, it will give you the subspace. Yeah. Okay. So if u is invariant under an operator t, then Tv belongs to u. That's just the definition of invariant subspace, right? Okay, and hence there is a scalar lambda in F such that TV equals lambda V. Right? This is completely trivial. Wait, what was it? ALS. Okay, A. Who was A? Oh, AD. Yeah, sorry, I shortened it to A because there was no conflict. It's clear. L. Is it clear? S. Okay, so more or less, I guess. Fantastic. Yeah, this is good. Okay, if it's not clear to you, please ask. It doesn't matter how many times it has to be repeated. Okay. All right. So what did I say? I didn't say anything very difficult. So all I said was, and it's just notation. So let's make sure we understand. So U is one dimensional, right? So suppose V belongs to U. Okay. So TV has to be inside U, right? But U is one dimensional, right? So the only thing that can happen is that this will be equal to some scalar lambda times the vector V itself. That is it. Is that okay? All right. So conversely, if TV equals lambda V for some lambda, some field, then span V is a one-dimensional subspace of V invariant under T. So the first statement was, suppose that U is an invariant subspace of dimension 1. Okay. So if U is a 1D, one-dimensional invariant subspace of T, then TV is going to be U. And what that means is that TV is going to be lambda V. That is the first direction we said. Okay. Now we're saying it the other way. We're saying suppose it so happens that you take some vector, you don't know where you got it from, you applied it to T, sorry, you applied T to the vector, okay, and you got some lambda times the vector, right? If this happens, then what do we see immediately? We see that dimensional subspace, right? Because we can take the span of V to be a subspace, and TV maps the vector V to the same subspace, right? So it's if and only if. Okay. All right. What was the ALS? Was it A L S? Clear? Yeah. Okay. Good. So now the equation TV equals lambda V is quite important and has specific names associated with it. Okay. And this is going to be a very important topic. Okay. When you do any kind of abstract algebra thing later in life, this is going to be very useful. And this notion, if you haven't seen it before, yes, most of you have probably, it's called an eigenvalue. Okay. So suppose T is a linear operator. A number lambda is called an eigenvalue of this vector T if there exists a vector V that is not zero, such that when you apply the transformation to this vector, you get some scalar times the same vector. Okay, so then this scalar is what is called an eigenvalue of the vector T. Okay, is the definition clear? ALS, A was fine, yeah. Exactly, good point. Right, let's think about it. Let's take a diagonal matrix. Okay, so let's take a matrix one. Okay, so I should repeat the question. The question was, can there be more than one eigenvalues? Right. Reasonable question. I said, when something is an eigenvalue, the question is, can there be more than one eigenvalues? Okay. So what do we know so far? Whenever you're in doubt, one of the easiest things you can do is think about the simplest examples you have. Okay, and an example of a very simple matrix is a diagonal matrix. Okay? So let's consider the following diagonal matrix. So you have 1, 2, 3. Okay. Now, can you think of any vector that would, any one-dimensional subspace of this? Okay, can you think of any one-dimensional invariant subspace of this matrix? So an invariant subspace is any subspace which maps to itself. One-dimensional means you have to think of one vector that maps essentially to itself with some scalar, right? So what happens if I multiply it with, say, 0, 1, 0? What do I get? Tell me the matrix multiplication. You got this? Do you want me to do it together? Okay, so let's do it together. Fine. So, okay, when you do the first one, you 0 times 1 plus row times column, right? What should I write? Tell me. What should I write? 0 times 1 plus 1 times 0 plus 0 times 0, right? What is the next entry? Plus 1 times 2 plus 0 times 0, correct? And the last one is also 0. Okay, so something to keep in mind, which is going to be very helpful. is that this vector is basically picking out this column. Okay, this is something very, very handy to keep in mind. So you don't actually have to do the multiplication every time. If the one is at the jth position, you're going to basically get the jth column as the answer. Okay, this you can check. It's a very simple matrix multiplication. Is that okay? What is it? ALS? LS? Is it okay? All right. So this is the jth column, right? So now let's do this again. So now that you know the given, so what is the answer going to be? The second column, right? What is the second column? 0 to 0. Okay. Now, can you write it as a linear combination, sorry, as a scalar multiplied with the initial vector? So this is the vector B. This is 2B. Okay, so you found an invariant subspace. Now, what is 2? It's an eigenvalue. Okay, so we got one eigenvalue. Okay. How about if we tried 1, 0, 0? What would we get? Right? Okay. And what is the eigenvalue of this thing? 1. And what about 3? Aaron, what does it tell me? Is it here? Okay. ALS. So A is fine. S. Good. Everyone in the neighborhood. I mean, it's just a representative. Making sense? So what is the answer to the question? There can be many eigenvalues. It doesn't have to be one potentially. Good. All right. So let's continue then. Any more questions about this? Okay, it's important. Getting the definition, understanding the definition is very important. Is it okay? Any questions? All right, so let's continue.
You say that every linear transformation that exists in eigenvalue.
That's one of the theorems. Really simple. Yeah, it's not obvious. It's not obvious. Good point. Because the question was, if I give you a linear operator, can you guarantee that there would be some eigenvalue? It's not obvious. Other than, of course, the ones we already said, like if you take the zero subspace, you get zero eigenvalue. Well, then the eigenvalue is probably no. The eigenvalue is defined for non-zero vector. Yeah, it's not. It's defined for non-zero, right? Yeah, it's defined for non-zero. Yeah, this is not clear. Yeah, it's a linear operator. It cannot map it to multiple things. Right. Exactly. So the question was, for a given P, can you have different lambdas? No. For different lambdas, you'll have different P's. Right? Like that's what this example was doing. Right? So there was one vector here, one vector here, and I didn't draw the last one. I didn't write the last one. Right? So there are 3 different vectors, and for each of them, you're getting 3 different lambdas. Eigenvalue can be 0. That is true. Okay, so the question was that if you have null space, right? Null space already looks like a very nice example of something that would have a 0 eigenvalue. Right? Because a null space report is just saying if you have some vector alpha, you multiply t with it, you'll get 0 times alpha. Right? That's what a null space is. So as long as the null space is non-trivial, you already have a bunch of 0 eigenvalues. But if there's no null space, then it's not clear that the eigenvalue is 0, right? Because this has to be non-zero vector. You cannot just say that, I'm sending the 0 vector to 0 and therefore getting the values. Okay. Now, some remarks. So it is important to require that V is not 0. Okay, of course, this is what we just said. And based on the discussion above, we have that above. We have that T has a one-dimensional invariant subspace if and only if T has an eigenvalue. Right? This I already argued earlier. Right? We saw more direction. We said if there is a this is the discussion, right? So one-dimensional invariant subspace implies that there exists a vector such that TV is lambda V, which means that there's an eigenvalue. And conversely, if there is an eigenvalue, right? So if TV equals lambda V, then there exists a one-dimensional invariant subspace, right? We just showed. So that's just a summary. Which one was it? Your S, right? Is it okay? Okay. So let's move on. Everything's clear so far? Making sense? All right. So let's do proposition 5.6. So proposition 5.6 says, I should also mention that in the text, he doesn't use the word proposition or theorem or anything. I'm just using it because we've been using it all along. tries to keep it a bit more informal because he just says statement 5.6. Okay, so proposition 5.6 is basically going to give you equivalent conditions to be an eigenvalue. Okay, so suppose V is finite dimensional and T is a linear operator and lambda is F. Okay, so this is fine. So you have vector space, T is going from V to V. Okay, and lambda is in the field F. It says that the following three things are equivalent. Because the first thing is that lambda is an eigenvalue. Okay, so this is the first thing. Second thing is that these three actually we have seen in a lot of detail when we were in Hoffman, right? So this is saying that, you know, what you're doing is instead of considering the operator T, what we're going to do is, so we have TV equals lambda V, right? This we already have. How can we rewrite it? We can rewrite it as TV minus lambda V is 0. Right, you can do this. It's completely fine. These are linear operators. This you can also write as T minus identity. Sorry, lambda times identity. V, right? You can do this. So now, if you look at this object, this operator, let's call it T tilde. Okay. So does T tilde? So okay. So if T has a non-trivial, so if V not 0 is such that it's not 0 is such that this condition holds, right? What can you say about T tilde's null space? So the null space has at least one element, right? There's one vector that is being mapped to 0.
We always the also belong. Then have vector B such that T of V is equal to the lambda. Even that vector belongs to the space.
Exactly that vector. At least that vector belongs to the null space of T tilde, right? Is that okay? Did I lose anyone? Okay. What was it? HLS? No. What was the acronym? DLS, right? ALS. Damn it. It was AD. Okay, thank you. A. Is it good? L? S? I'm assuming the others are also okay. We can have more representatives if you need, okay? But for now. Louder. How is T tilde? No, I'm saying null space of T tilde. So the null space of T tilde, what is the null space of a vector, right? The null space is defined as what? So there's some operator say O, right? The null space of this is defined as alpha such that T alpha is 0. Oh, sorry. Let me not call it. Let's call it T tilde. Is that okay? Okay. Come on, you cannot ask me that question. We saw that, right? Remember this? We defined linear combinations of linear operators, and we said that there's a space of linear operators, and we showed that linear operators, like their sums are also linear. It's identity times lambda, right? So T, you agree T is a linear operator. You agree lambda identity is a linear operator, right? So the combination is also linear. Okay. I haven't done that yet. I'm just building intuition. I haven't proved this. Okay, I'm just trying to tell you how we're going to think about it. So I'm saying, okay, so this is a statement somebody gave us, and there's this strange T minus lambda identity appearing. So I was trying to motivate why we should consider this object to begin with. Yeah. Okay, so what am I saying? I'm saying that if there is a vector not 0 such that TV equals lambda V, right? Then one can consider this T tilde operator and note that the null space of T tilde is going to be exactly, or has to be at least, so the size has to be at least 1, right? Size being dimension, right? It has to have at least one element, correct? Okay. And we remember that for something to be 1-to-1, right, it was equivalent to saying for a linear operator, okay? It was equivalent to saying that the null space is 0. Do you remember this? Right? Because if this doesn't happen, you can take the difference, right? If there are two distinct vectors that are mapping to the same thing, you take the difference, and that belongs to the null space. Yeah. Right. So if t tilde alpha was the same as t tilde beta, right, then alpha minus beta acting on t tilde is what? Is 0. So the null space is non-zero. Right? Is that okay? ALS, L, S, yeah. Yes. No. Lambda is not a matrix. Lambda is just the scalar, right? It's the eigenvalue. Lambda is, yes. Yeah, it's a linear transformation, right? Remember we studied that if you, that was somebody else's question as well. Who was asking? You were asking it. Symmetry, but you can take its matrix representation if you're looking at matrices, but otherwise this is the operator that sends all vectors to itself. Yeah, we'll come to that. So at the moment, I'm just trying to motivate that this t minus lambda I, right? This operator, so t minus lambda I, the null space of this thing, I'm saying is related to whether t has, so is related to whether t has lambda eigenvalue, right? This is what I'm trying to show now. I'm just trying to show you intuitively, right? That if it does have an eigenvalue, then this null space has to be greater than at least one, like this dimension. Right? So that's a very nice connection because then we know a lot of things from the null space, right? You have the entire rank nullity theorem, you know, all of those things. And from there, we immediately have that. So you remember this statement, right? So if t is 1 to 1, it's equivalent to saying that the null space is 0, right? So now you're getting all the nice properties that you've already studied. Okay. So if lambda is an eigenvalue, then that would imply that this thing is not injecting, right? Because 1 to 1 and null space I just said are exactly related. Injective is 1 to 1, right? So it cannot be 1 to 1 because the null space has some non-trivial vector. Yeah. And then the rest of them are, these are things we've already studied. So we're not going to spend too much time on this. And this is just essentially the rank nullity theorem and all those statements essentially give you this. So we've already covered this. Is this okay? So if you just understand these two, A and B, the rest are very straightforward. A. Good. All right. L. S. S is not convinced. Are you sure? If something is not clear, ask. Okay, so we move on after this. Is there a question? Tell me. Is it open? Okay. All right, then let's continue. All right, so definition 5.7 is eigenvectors. So we already defined eigenvalues. Okay. Also, actually, I should maybe also mention, eigen is a German word. Okay, it means characteristic or my own, something like this. So it's basically saying it's some important property of the linear operator. Okay, so that value is somehow the operator's own value. So, okay. So eigenvalue, eigenvector. So eigenvector says the following. So suppose T is some linear operator and lambda is some field element, right? So T is a linear operator as usual. Lambda belongs to F, is an eigenvalue. Okay, is an eigenvalue. So if you're given this, the vector V, which was giving you TV equals lambda V, so this vector V is called an eigenvector. Okay, so vector V is called an eigenvector corresponding to lambda if this condition is satisfied. Okay. So these are just different names for the one-dimensional subspaces, nothing very complicated. L, S. Okay. Okay with everyone else? Yeah. Okay. Right. So now, so it says since TV equals lambda V, if and only if T minus lambda I V is 0. Like this we just saw, right? You can just write it down as TV equals lambda V, if and only if TV minus lambda V is 0, which is equivalent to writing T minus lambda identity. Right? This is fine? Yeah. Okay. So this is the case. It holds that a vector V which is non-zero has an eigenvector of T corresponding to lambda if and only if this vector actually belongs to the null space of T minus lambda. This is what we were discussing, right? In the previous thing, we were saying that there is a vector V such that you get T times V giving you lambda V, right? Then we know that T minus lambda I would have that as exactly like the null vector, right? It will be in the null space. Is it clear? Okay, so who wants to show me how V belongs to the null space of T minus lambda I?
Payments lambda is not okay. So if our 360 can be
Perfect. Anyone else? ALS?
applying T minus lambda and T, I can split it, open the parenthesis, say, on the other side, so T of B is equal to lambda B.
That's exactly. Very good. Okay. A, got it? L, S. Okay. So let's continue. Okay, so now there's an illustration. So it says, suppose that T belongs to L. How much is left? Proposition 5. Okay, let's try to finish this section. It's okay. It's okay to go a little bit slower in the beginning because it's important to get the definitions in place. Then it'll be much easier to have some intuition about the statements. Okay, so okay. So let's look at an illustration here. So it says, suppose T belongs to LF2 is defined by the following. So T WZ is just the definition. Okay, it takes the first element as a minus sign and maps the first element to the second element. Okay, it's just a linear operator. Okay, so we want to find the eigenvalues and eigenvectors of T if F is real. Okay, and the other one is finding eigenvalues and eigenvectors if the field is complex. Okay, so remember I mentioned earlier that it matters what the field is, right? Whether it's real or complex, it can change whether it would have an eigenvalue or not. So we'll see it in this example. So we'll see it in this example. All right. So okay, so this is an intuitive argument. Okay, this is not supposed to be a proof. The proof we'll do in just a moment with algebraic equations. So suppose F is just a set of real numbers, then T can be seen as a counterclockwise rotation by 90 degrees in the plane R2. Okay, so what does that mean? So suppose I have some vector here. Okay, so suppose its coordinates are, let's say, let's call it Z and W. Okay, so if you rotate it by 90 degrees counterclockwise, so you'll have some vector like this, right? Yeah, and you can check. This is like just trigonometry, okay? This is basic stuff. You can check that this. So yeah, what would be this height? This distance. It would be double, right? And the height would be Z. Like just intuitively, right? Because if you take this thing very, very close, this height will become very small and this W will become very small. Right? No. Is this doing a rotation? ALS. Is it okay? No, ask if something is not clear. That's the whole point. Okay, let me do it a bit more intuitively. Okay, let me draw it a little bit better. So suppose this is, so this distance is, say, this distance is, say, Z. Okay, and this height is, say, W. Okay, if you rotate this vector by 90 degrees counterclockwise, right, it would look like this vector, correct? Just intuitively. Okay, is that okay? Right? No, it's just rotating it counterclockwise, 90 degrees. So this is a 90-degree rotation. So this distance, so this was W, this will also be W. Okay, this you can check. And this height from here to here, this height would be Z. Okay, isn't a rotation? It's nothing complicated. Not convinced. S is not convinced. S, is it okay? Are you sure? No. This is trigonometry. Okay, I'll give it to you as an assignment. Okay. So this is just a claim. So basically, what it's saying is if you take this vector with components z and w, you rotate it counterclockwise by 90 degrees. What the final vector would look like. You can use trigonometry to do it directly if it's not all that clear. Okay. Okay, but why am I saying this? I'm saying this because let's look at what this this operation is doing, right? So this operation takes a vector with coordinates w, z, okay, and it maps them to what? Minus z and w. Okay, so I have to swap my z and w into the language. Let's call it zw. Okay, depends on your choice of coordinates or whatever, right? So now you see it's mapping this zw to minus wz, right? And which is exactly the coordinates of these guys, right? So it's minus w here, and then z for this vector. And this vector is z. It looks like I lost a bunch of it. Okay, doesn't matter. This was just for some intuition. If you don't get it, that's fine. We'll do it algebraically as well. The crucial point here is that you can take this on faith, okay? You can believe me for now that this is what the representation is. Okay, it's just a counterclockwise rotation. Now, it says an operator has an eigenvalue if and only if there is a non-zero vector that is sent by the operator to a scalar multiple of itself. Is this fine? Is what we just discussed, right? Okay. However, a 90-degree rotation of a non-zero vector in R2 can obviously never be a scalar multiple of itself. Right? Because if you're rotating vectors, no vector is going to be mapped to itself if you're rotating it in two dimensions. Right? Is that statement clear? So if you have a rotation, right, you're never mapping any vector to itself. You're rotating all of them. Okay. So no non-zero vector can be mapped to itself. And so therefore, what I'm saying is that if the field is real, T cannot have any eigenvalues. It's a very geometric, very simple proof. Not a proof. I mean, it's an argument. Like you just have to prove it, but that's not exactly. Does that make sense? Yes. If you assume that statement, okay, so I understand that statement is not clear that it's a rotation, but assume that it is a rotation. So if consider any operator T that's a rotation, then it's clear that you cannot have two dimensions. You cannot have an eigenvalue. Is that okay? In 3D, of course, that's not the case. Because in 3D, you can have like, there's the actual vector, right? That will not get rotated. So that will be an eigenvector. So there will be one actual vector, right? Along which you're rotating. So that will stay unchanged. So that will okay. All right. So point B now is saying, okay, so we understand with reals you cannot have an eigenvector, eigenvalue. Let's see what happens if you take it to be complex. Yeah, now we have to do it algebraically because we cannot really draw things in complex or easily. So to find the eigenvalues of T, we must find scalars lambda such that the vector acting on WZ gives you lambda times the same vector. That's just the definition. Yeah. Okay. Okay, so the equation above is equivalent to simultaneous equations. So we can just expand it, right? So TWZ was doing what? It was giving us minus ZW, right? That is the transformation, correct? And we want this to be equal to lambda times WZ, right? So component-wise, if we equate them, right, what do we get? We get minus Z is lambda W and W is Z, right? So minus Z is lambda W, W is. Did I mess up? Oh yeah, I forgot the lambda. Thank you. Okay. Yeah. S. L. Okay, good. So substituting for the value, substituting the value for W, right? Given the second equation into the first equation, gives us the following. Okay, so this is just algebra. What we're going to do is we're going to substitute, and we'll get minus Z is lambda square Z. How do we do it? Yeah, you can just eliminate W, right? So you get this. And now we know that Z cannot be 0, right? Because if Z was 0, then according to this constraint, W would also be 0. Yeah. If z is 0, w will also have to be 0. And we want a non-zero vector. Right? We cannot have a 0 vector. Otherwise, when we talk about eigenvalues, it has to be non-zero. Is this step clear? That z cannot be 0. All right. So since z cannot be 0, 5.9, yeah, this is the equation. So because z cannot be 0, then the only other option is that if you solve this equation, you can divide it, right? Since z is not 0, this would give you that -1 is lambda squared. Okay. And you see that you don't have solutions in duals. Right? So the geometric argument was like just an argument. But here you see algebraically that it cannot have a solution. Okay? By being complex, you cannot have a solution. Okay? Cute. Is it sort of nice? Yeah, so let's try to recall what is the definition of an eigenvector? Can it be 0? So we just said that. Right? So yeah, we said the eigenvector cannot be 0, right? Otherwise, you can have any eigenvalue. Right? Okay. Perfect. All right. Okay, so this is what you get. And the solutions are, of course, I and minus I. This we know from our previous studies. And you can actually check that the eigenvector, that you use the solution, plug in the value of z, sorry, not z, w in terms of lambda, right? So z and w are related. You plug in the values, and you'll see that w comma minus wi and w comma wi are indeed eigenvectors. Okay, with the corresponding eigenvectors. Okay. It's kind of interesting, no? You should think about it. It's a rotation in reals, so it cannot have an eigenvector, but in complex, it has eigenvalues. So it's sending vectors that are.
House like sort of a rotation. He made something case diagram particular by
Yeah, there are some connections. I haven't thought about it very carefully, but I'm sure there are some connections.
e to the power I each other with I.
Yeah. Those you're treating the real and complex as that just the complex field. That's a little bit different. Here we're saying that the operator itself doesn't have eigenvectors. Yeah? Okay, so you should be very happy at this point. You learned something very new. Okay. All right. So let's continue. Right. So we now show that eigenvectors corresponding to distinct eigenvalues are linearly independent. Okay, so now we're sort of combining all the concepts we've learned. We've learned linear independence, we've learned null spaces. Now we're combining them to understand the structure of the operator using eigenvalues and so on. So now we're going to say that if there are distinct eigenvalues, then the corresponding eigenvectors are going to have to be linearly independent. Is the statement of what? Yeah. So formally, how do we write the statement? It says let T be some linear operator. Okay. And suppose lambda1 to lambda m are distinct eigenvalues. Yeah, so these are distinct eigenvalues. T. Okay. And suppose v1 to vm are the corresponding eigenvectors. So we want to assert that v1 to vm are linearly independent. Is the statement clear? Yes. Yeah. For everyone? Okay. All right. So let's see how to prove this. So we're going to prove by contradiction. So suppose that v1 to vm are linearly independent. Oh, sorry, linearly dependent. Right? We want to prove that they're independent. So let us assume for contradiction that they are linearly dependent. Let k be the smallest positive integer such that vk is in the span of v1 to vk minus 1. So it is linearly dependent. So it has to happen at some point, right? Like you have to be able to write one of the kth vector as a linear combination of the groups. And this has to happen for some k. That is guaranteed. So suppose k is the smallest such vector, smallest such index for which this happens. Okay. So then we know that there exists a1 to ak minus 1 such that vk is a linear combination of the remaining vectors. So far so good. Yeah. Okay. Now we are going to apply t to both sides of this equation. Okay. So if you apply it on the left and the right, what do we get? We know that T acting on Vi is lambda I Vi, right? Because these are eigenvectors, remember, right? So because they're eigenvectors, the action is just the same as adding these scalar eigenvalues. Is this step okay? Okay, so in case you fell behind, the argument is as follows. What we're going to do is we're going to show that the vectors v1 to vn are, sorry, we're going to assume that they're linearly independent. Okay? We want to show that they're independent, but for contradiction, we're assuming that they're linearly independent. So if you make that assumption, what is so one can conclude that there has to exist some integer k such that vk is in the span of the remaining vectors. Okay, so you choose the smallest such k. Okay. So once you have this, we can write it as a linear combination more explicitly. So we can write vk as a linear combination of the vectors. Is that fine? All right. And now what we're going to do is we're going to apply t to both sides of this equation. So we'll apply t here, and we'll apply t here. And we know t is, oops, sorry, we know t is linear, right? So this basically amounts to writing tvk equals a1 tv1 plus a2 tv2 and so on, right? Is fine. And we also know that vk's are eigenvectors, right? From the hypothesis of what we're trying to show. So therefore, tvk can be written as lambda k vk. tv1 can be written as what? Lambda 1 v1 and so on, correct? Okay. So we have this expression. Is everyone okay until here? Any question until this point? Yes? Can you move just a little bit to the left or right? Is it clear? Sure. Okay. All right. So we have this equation. Now we're going to multiply both sides of 5.12 by lambda k. Okay, I'm allowed to do that. So I'll multiply both sides by lambda k and subtract from the equation above. Okay, so we're going to take this equation. We'll multiply this by lambda k on both sides and subtract. Okay, so what happens to the left-hand side when you subtract? The left-hand side disappears because you're subtracting lambda k vk from lambda k vk. So there's no left-hand side. On the right-hand side, what is going to happen? Each of these coefficients is going to pick an additional lambda k. So you will have lambda k minus lambda 1, lambda k minus lambda 2, and so on. Is that fine? Okay. So this is okay. All right. Now, since we chose k to be the smallest positive integer satisfying this equation 5, which is 511, which is this one, right? So we chose it to be the smallest possible k for which this holds. It follows that v1 to vk minus 1 are linearly independent. Okay, so what did we say? We said choose the smallest k for which the vector vk can be written as a linear combination of the vectors before. Right? So it means obviously if there was, that's the first time it's happening. All the previous ones are linearly independent. Right? Otherwise, k would have been like k minus 1. Is this statement clear? KLS? A? Yeah? Yes? It's not clear? Okay. So here what, so let's see. So the statement we said was let k be the smallest positive integer such that vk belongs to the span of these vectors, right? So what does that mean? It means that these vectors are already linearly independent, right? Because if they were linearly independent, then vk minus 1 would satisfy the same property. What we are saying is the smallest k such that this property is. We'll give you a few seconds, okay? If you have any questions, you can ask. Is this clear to everyone? This statement? Yes. What is the confusion? Tell me. It's good. Others might also have the same problem, right? Tell me. Is this statement the issue or is something else? No. What is given? Okay. So what we want to show is that all of these vectors are linearly independent. That is what we want to prove. So we want to say that if you're given a bunch of eigenvectors with distinct eigenvalues, those eigenvectors are linearly independent. The eigenvectors we are calling v1 to v2, right? Okay. Now, To prove this statement, we are assuming for contradiction that V1 to Vm are actually linearly dependent. Yes. Are you getting confused later? Okay, got it, right? Okay. So all right, just to get everyone back on board. So this statement is clear, right, to everyone that there is some smallest case such that Vk is in the span. In particular, this means that V1 to Vk minus 1 are linearly independent. Is this statement okay? Yeah. Okay. And then from the argument that we were writing down, we have this equation, right? This equation is showing you what? It's showing you that V1 to Vk minus 1, there is some linear combination that is 0. What does that mean? It means that they're linearly dependent, right? But that's a contradiction because we already assumed that we already said that those vectors are V1 to Vk minus 1, they're linearly independent, correct? So now from this, you're getting a, okay, so it would give you a contradiction, right? So to not get a contradiction, what we have to do is we have to make sure that all of these guys are 0. Oh, sorry, one of these guys is, wait, eliminate. Okay, so we have to have that all of these coefficients are 0, right? So you have to have the coefficients of each of the V's to be 0, right? And we already know that the eigenvalues are distinct, right? This we already assumed. So the differences cannot be these lambda I minus lambda j, they cannot be 0 because they're all distinct, correct? So the only thing that can be 0 are these coefficients, A1 to A2. Is that okay? All right. So this means that the A's have to be 0. Yes, I think I lost you again. You got it? Okay. A, L, all right. Okay, so this has to be, so the A's have to be 0. And recall that lambda k is not equal to any of this. Okay. And that in turn implies that Vk is a 0 vector. Right? Because Vk was, so Vk, remember, was this vector, right? This is Vk. So if all these A's are 0, then Vk becomes a 0 vector. Right? But Vk is an eigenvector, so it cannot be 0. Okay, so that's how you get the contribution. Okay. So you can go back and take a look again, okay? Because I've told you the little steps. You can stitch it together once for yourself to make sure that it sort of makes sense. Okay, so let's continue. Oh, all right. So the corollary below states that an operator cannot have more distinct eigenvalues than the dimension of the vector space on which it acts. Okay, this I'm going to leave as an example. Yeah. Sorry. I should have clarified this. So here, so T is a linear operator. Okay, and lambda 1 to lambda m are distinct eigenvalues of the linear operator. We understand the definition of eigenvalues, right? It's just T times some vector gives you lambda times the same. Right? And V are the corresponding eigenvectors. So in particular, what this means is, so I mean, essentially, it's equivalent to saying that T acting on Vi is lambda I. Okay? And we are assuming they're distinct. Okay, this is important, that none of the lambdas repeat. Because, for example, if you take, say, the identity matrix, right, it has eigenvalue 1 for all eigenvectors. So it can repeat. But here we are taking operators such that the eigenvalues are distinct. Okay. For you, I don't need to ask. All right, good. Okay. So now what we're going to do is, yeah, so we are now asking, okay, so suppose an operator, yeah, okay, let me just state the corollary. So suppose an operator, the vector space is finite dimensional, okay, as our favorite kind of vector space. Then each operator on V has, so each operator on V has at most dimension of V distinct eigenvectors, eigenvalues. Okay, why is that? So what did we show? We showed that if you have distinct eigenvalues, the corresponding eigenvectors are distinct, okay, or are linearly independent. Or also distinct, but linearly independent. right? So if you have a vector space of dimension, let's say dimension n, so suppose this is n, can you have linearly independent vectors more than n? Can you have more than n linearly independent vectors? Okay, so that's the proof, right? Okay. Okay, perfect. We have like 30 seconds left. Not good. So let me quickly give you the definition, I guess, and then we can continue from next time. So, okay, so let T be a linear operator and U be a subspace of V invariant under T. Okay? And suppose U determines two other operators. Oh, sorry, then U determines two other operators, T restricted to U and T acting on the quotient of V. Okay, this will take some time. It's fine. Let's stop here. It's fine. It will not make sense. Yeah, let's do it. Okay, thank you so much, you guys.